So hello everyone. Today I present a work I've been doing with Guillaume Charpiat and Sylvain Chevalier. So with Guillaume and Sylvain, we are interested by the architecture of neural networks, and more especially, we are looking for an algorithm that will iteratively increase the size of the neural networks until it reaches a certain accuracy. So in this presentation, I will first start by introducing what are the common practices when it comes to constructing architectures. Then I will present how we decided to solve this problem by defining what we call expressivity bottlenecks. And thanks to this definition, I will define what is the best parameter move for each layer L, and then what are the best neuron nodes to add at each layer L. And if I have time, I will present some results and do a little conclusion. So what are the common practices? So usually we take very huge architecture because they enjoy two nice properties. The first one is that the functional space that is described by this architecture is large enough to approximate or to be close to any function you would like to approximate. And also the second property is that even if the problem is not convex in the parameters, you can still follow the gradient descent, and the parameter you will have at the end have nice properties. So here is a little figure to explain. So in purple, this is the functional space you describe with your architecture. And then you follow the gradient descent and you achieve a minimum which has good properties compared to the best one you have inside this parameter space. But having like a big architecture might be a burden, so you would like to shrink your architecture. A very easy way to do that is to do pruning. And pruning is just apply a mask on your trained architecture, and the mask will tell you which connection has to be removed and which one has to be kept. And at the end, you have a sparse neural network which consume less energy. But with Guillaume and Sylvain, we want to do the other way around, which means that we want to start with the very tiny neural networks and make it grow until it reaches a certain accuracy. So just before presenting the formulas, we are doing neural architecture search. And there is two categories in this field, and we are working in the first one. And the first one is from scratch, which means that we focus on one specific task, and we don't use the knowledge you would have on other tasks to decide which architecture we might use, compared to the other one, which is more like transfer learning, when you use the knowledge on other tasks. So by doing so starting with a tiny architecture and make it grow, we hope to do a faster learning, use less memory and less energy. But we have to face two problems. The first one is that as we deal with very tiny neural networks, we don't enjoy the two properties I talked about before. And also the solution which is given by the gradient descent is very poor. So we will need to use other objects to move inside your parameter space. And another problem is when you decide to increase the size of your architecture, you have many possibilities. And so you may have to do some trial error tests, which might be very energy consuming. So we need to define a metric, which is expressivity bottleneck, that will help us with that. So what is expressivity bottleneck? When I define expressivity bottleneck, I need to define also where they are, and I need to quantify them to tell which part of the architecture suffer the most from expressivity bottleneck. So just some notation, I will use the dataset as xi, yi. The network will be f of theta, with theta the parameter of the networks, and the loss function will be calligraphic L. Okay, so to define expressivity bottleneck, I need to define two functions. The first one is called the desired update for the function f theta, and the second one is called the possible update for the function f theta. So for the first function, it's defined the same way you define the gradient for the parameters. It indicates the direction on which you want to go for the function f theta in order to decrease the loss. So the same way you define the gradient as the direction on which you have to go for the parameter in order to decrease the loss, you define this desired update as minus the derivative of the loss, but according to f theta taken at point x. And on the other hand, you have the possible update, which is just when you move from parameter theta to parameter theta plus delta theta, what is the functional movement you implies, which is just the derivative of theta according to theta multiplied by delta theta. So just to give you a little example, so here you're doing a linear regression, so in blue, and you try to predict the red line. And so the f theta is just theta transpose x, and you use the square loss. And if you try to evaluate what is the desired update at point x, you derive the loss according to f theta, which is just theta transpose x. And you obtain this formula. And as you can see, sorry. No, this one. Okay. Okay. And so, for example, as you see, at this point, the prediction is above what I should have predicted. So this quantity here is positive, minus this quantity is negative. So it already indicates that at this point, the function wants to go down. Here on the inverse, you have what I should have what I predict is below what I should have. So this quantity is negative, minus this quantity positive. And it indicates that I want to go up at this point. And on the other hand, you have the possible update. When I move from theta to theta plus delta theta, then the function, the prediction, which is theta transpose x, move from delta theta transpose x. So just to do a little figures, if you have a certain architecture, then you have a certain functional space which is associated to it, which is the purple era here. Then you initialize your parameter. It gives you a network inside this tangent space. Inside this parameter space, this functional space. Then you define what we call the tangent space in f of theta, and this tangent space is just all the function that can be described as equal to f of theta plus the derivative of f according to theta multiplied by delta theta. Actually, this is an approximation of all the function you can achieve when you do a gradient descent. And so in this functional space, we can represent the desired update because it is a movement in the functional space. It indicates in which directions you want to go. And you can also define what is the projection of this function on the tangent space. And actually, we call the expressivity bottleneck the distance you have here. So the difference in what you want, in direction you want to go, and what you can actually do. So mathematically speaking, this is the minimum of the expectancy of the distance between the desired update at point x and the possible update. And in fact, you minimize over the possible update in the tangent space. So now let's go back to neural networks. Well, I will present the theory only on feed-forward neural networks, but the theory is the same for convolutional neural networks. So I have the buckle just retain that the the post-activation function is B, and the pre-activation function is A. So you have A, nonlinearity sigma, B, then WL for the weight matrix, and etc., etc. And then the output is just f of theta of x. So the same way I defined the desired update for the function f theta, which is the output of my networks, I define also the desired update for every pre-activation function AL, and this defined the same way, which is minus the derivative of the loss according to AL taken at point x. And I also define the possible update, which is what is the functional move implied by changing from parameter theta to theta plus delta theta, and it is just derivative of AL according to delta theta to theta multiplied by delta theta. Okay, so now with all this definition, I can define what is the best parameter move. So the best parameter move is just finding actually which parameter is associated to the projection of the desired update here. So there is two ways of solving this problem. You have the simple one, which is on the top, and the most complicated one, which corresponds to the real definition of minimizing the expressivity bottleneck. The second one, so the one we saw before, is when you try to minimize the distance between desired update and possible update, but by moving the parameters for all the architectures. But this is a very complicated problem, so we simplify it by only considering movements of parameters in the layer L. So in the figure, the simplified problems correspond when you try to minimize the expressivity bottleneck at layer L by only moving those parameters, because the second program is too complicated and non-convex. So if you look at the solution of the problem, it's pretty simple because when you move from omega L to omega L plus delta omega L, actually the functional change you imply is just delta omega L multiplied by BL minus 1, as you can see here, because omega L multiplied BL minus 1. And you try to minimize the distance between desired update and this functional movement, which implies that the solution is exactly the same as doing a linear regression from BL minus 1 to desired update. So this is what is the best update at layer L if you want to decrease the expressivity bottleneck at layer L. So now I define the best neuron to add. The best neuron to add is doing kind of the same trick. So I still want to decrease the expressivity bottleneck at layer L. And so I decide to add neuron at layer L minus 1 because it will imply a functional chain at L. So if I add, for example, 2 neurons here, I have like the input weight, which is equal to alpha and output weight omega. And then if I add, so here k is equal to 2, the functional change that is implied is just the sum over the number of neurons of the scalar product between alpha and BL minus 2 remultiplied by omega L. So when I redistribute all the information at layer L. So actually we simplify this expression by saying that alpha is very small. So we linearize this formulation and it becomes this. So the possible update when I add those neurons and I move alpha and omega you have here, the functional change that is implied by this change is just a linear form of omega and alpha. So actually to have like, to be consistent, you have that your nonlinear function has to be 0 at 0. Otherwise you cannot do this Taylor expansion and express the possible update like this. So now we solve the same problem. So we try to reduce the expressivity bottleneck at layer L. So we try to minimize the distance between the direction in which we want to go, what I can do with the current architecture, and what I can do when I add neurons. So the current architectures give information using BL minus 1, L minus 1, while adding neurons use the information I have in BL minus 2. So actually, I know the way we compute the solution is not the best one, but I could explain why we do like this. First, we estimate delta omega L as we did before. And we compute this variable, which is the projection of the desired update, but we will not compute like the regression in one time. So we estimate first delta omega L, and then we estimate big omega and big A. And so once you've computed delta omega L, you have so this quantity, you try to once again do linear regression between BL minus 2 and the projection of the desired update. And actually, so the solution is the same way you had before. It's the form of the linear regression. And actually, you could take like output weights omega and input weights, anything that looks like a SVD of F star. There is many solutions that can switch to input and output weights. Actually, we took a very special solution because they have a good properties. We also use the covariance of BL minus 2 and the covariance matrix between L minus 2 and the projection of the desired update. But we do an SVD on this function. And we define the best neuron to add using those matrices, the eigenvalue you have on the SVD here, and the matrix here. And the advantage of this is that if I decide to impose a rank for this matrix F, so I just want to add one neuron instead of adding all of them, then this solution is always is still the best one. Because if I took like any SVD of F, I have to consider having having all the possible neurons I can add. And if I decide at the end to add only one neuron, then the solution I have is not the best one. But what is great is that every neuron I had decreased the expressivity bottleneck by the square of the eigenvalue you had on this matrix before. And the loss is also decreased by the same amount. So you can decide whether or not to add neuron, and that's why the previous solution is better, is that once you computed the eigenvalue, you say, okay, the last eigenvalue are not interesting, I decide to only add the 2 or 3 first neuron, and so then the solution is still the best. The reason why you have like a similarity between those two equations is because when you do a Taylor expansion of the loss, actually, once you have added the neuron, the loss is equal to what it was equal before, minus the scalar product between the desired update and the possible update. And actually minimizing the distance between two objects is the same as maximizing the scalar product given a certain constraint on one of the objects. You have only one paper which is very close to us, but actually it only sees the problem as reducing the loss, so it doesn't project on the architecture, and also it doesn't have the same constraint, so you have many matrices that disappears. And also you don't have, they take the SVD, not caring that if you impose a rank on the matrix, it changes something. So we try, just a little recap. What we try to do is try to reduce expressivity bottleneck at each layer. We first need to compute the best parameter move, and then we need to compute the best neuron to add. And knowing that the graph can grow exponentially because the number of neurons you can the maximal neuron you can add is linked to the rank of this matrix, and so it grows exponentially if you decide to add all neurons every time. Just to show you little result, I think this is. I still have time. How many time I have? 4 minutes. Oh, nice. Okay, nice. So this is result, for example, we have on a Cypher10 database. I cannot really see. So train FS is from Crash. It's like, so we take, okay, first we take our method. So our method is in green for train and red for test. So in black, you have the number of parameters, which is increasing. And then you have like the train we have good performance on the train, and then the test stagn. Knowing that the architecture we have is conv max pool, it's two ResNet block, then two linear layer. So it's a very simple architecture. That's why you cannot achieve 100 accuracy. And you have in comparison a model which is trained from scratch, which means that we take the architecture we have achieved at the end, we reinitialize the parameters taking k-mean normal, and we train from scratch. And as you can see, you have kind of the same performance. This is on this dataset comparing adding neurons with adding random neurons. So in blue, you have the loss at time when you don't have neurons. And in green, it's when you had neurons, random neurons, and in red, it's when you had neurons with our method, in terms of epochs and in terms of seconds. And you have the accuracy on top. Here is an example also on the MNIST dataset. I think it's only a two linear layer here. So we grow a neural network using our method. We achieve a neural network which is 150 for the 100 for the first number, 100 neurons for the first hidden layer, 50 for the second one. Same for the ALEA. We are trained from crash by initializing. And here is the same. We take the architecture, but we compare to a very big neural network in red here, when you have 1,000 neurons per layer. And as you see, it takes a long time to train, but even if at the end you know that it's going to have the same performance on both. Thank you.
All right, are there some questions? Okay, two, great.
Thanks for this very interesting talk. It's also a special interest to us to basically make the training of greens functions green. You have at a certain point with expressivity, you made a model choice, which I could understand from the optimization point of view. You looked at the fixed layer, and not at the past for the expressivity.
You mean the parameters in the previous layer?
Yeah. Yeah. How harmful is that? I mean, I understand
that
you do it from the mathematical point of view,
yes.
But from the applied point of view.
You mean the fact that we simplified the problem here?
Yeah.
We didn't evaluate it, But you're not the first one doing the remarks, so I think we should evaluate it. Yes, but it will need to do like a gradient descent on all the parameters you have just after. It's just like training your neural network actually. But yes, I don't know how harmful it is.
Can you think of experiments to
Yeah,
check
so
this
you
out?
just perform like your object function is actually the desire update, and you just do like a back propagation on the parameters you have before to match the desire update for a special batch size, for example. Yes, it could be a simple experiment.
Okay, thank you.
You're welcome.
Thank you for your talk. So I have two questions. So the first one is only if there is some impact of the non-linearity in your approach, because it's not.
In fact, you mean if we decided to do on BL instead of AL?
No, I mean it's all sigma L is a non is a ReLU or something like that. So, I mean, you change the
Oh
activation.
yes. Actually, we use SOLU in the experiment, but we also try to do it with the ReLU, and it works.
But in theory is.
The theory is that we, instead of using the gradient, we should have like a subgradient.
Yeah.
But the thing is that the desire update is not well defined. The desire update, it is a derivative according to a function that is not continuous. It might be not defined.
Okay.
So you will have to define a smooth function. You often do that in optimization. You define a smooth function which is just below your function, and you decide to do as it was your function.
And yes. Yep, sorry. No, that's a short question. Is there is, I mean, in your way you are adding neurons, but there is somehow a way to add the layers?
Yes, we are working on this actually. But the thing is that we add layer when we decide that there is no linearity to exploit between the desire update. I mean, when the desire update cannot be a linear function of BL-1 and BL-2. You need to exploit the non-linearity, and so the problem has to be changed, and the optimization might be different. Okay, thank you.